Synchronous motors. Why does adjusting DC excitation affect stator current and power factor? In this presentation, we're going to unpack a little bit behind the vectors and how this actually functions if we consider the application of what we already know about vector addition, Ohm's law, and magnetic flux interaction. We already know that there is a stator magnetic field and a rotor magnetic field. And we know that these two separate windings create their own independent magnetic flux paths. Now, what's important about this is that the coil, because it is generating a south pole at the top, has magnetic flux or lines of flux that are 180 degrees in the opposite direction than the stator lines of flux. And this is important because what it means is that the amount of total resultant voltage between these two interactions is going to be less than either one of the two. So E the stator and E the coil are actually working in opposition to one another. Because these magnetic lines of flux are actually traveling at different directions or opposing one another, it means that there will be a canceling effect. And the rotor magnetic flux will start to cancel some of the stator magnetic flux. The resulting voltage then, or E resultant, is what would be used to calculate the stator current. So I of the stator is actually equal to E resultant voltage divided by the Z of the stator winding, whatever that happens to be. Let's take a look at this in more detail. When we're maintaining DC excitation, but increasing the mechanical load, the vector diagram looks like this. The stator current is quite low, and A1 that we see there is actually equivalent to the torque angle. So the angle that the generated voltage from the coil is at. So it's a very low angle. Remember, we said that the resultant voltage is a product of a vectoral addition of E of the coil and E of the stator. This means that if there is pretty substantial or equivalent length or magnitude to each of these, that we should see a resultant that's quite low. A low resultant voltage divided by the Z should then result in a low stator current. As mechanical load is increased, we can see that the angle of torque that we see, or the torque angle, increases also. If the torque angle increases, that's going to have an effect on the vectoral addition of E of the coil and E of the stator. The resulting voltage, or ER, gets larger. And if ER gets larger, it means that I of the stator also will rise due to Ohm's law. Finally, if we increase it to the extreme, the torque angle gets substantial. And since it is so large, when we add vectorially E of the coil and E of the stator together, we have a resultant value that is much higher. The resultant voltage then divided by the impedance of the stator coil will result in a large stator current due to Ohm's law. What if we were to take a motor that had a constant mechanical load and it start playing with the actual DC excitation? So right now we have a synchronous motor and we have full mechanical load, which means we do have a torque angle. The torque angle is used to deflect or show the relative discrepancy between the coil voltage and the stator voltage. The resultant, as we saw before, is quite large, which means the stator current is quite high. If we were to increase the DC excitation, notice what has happened. Increasing the DC excitation has zero effect on the torque angle. Torque angle remains the same. However, what has happened is that the length or magnitude of the applied voltage has increased. Now, if the voltage is increased here, it means that when we do a vectoral addition of E of the coil and E of the stator, the resultant voltage will have shrunk. This means that the stator current has gone down. It is now in a leading power factor state and, as we can see, would be used for power factor correction. Remember that the stator current is always due to the E resultant, which is a phasor addition of the coil voltage and the stator voltage. In this way, a three-phase synchronous motor can be operated at any range from extreme lagging to unity to extreme leading.